Welcome. We will now go through the third week's assignments and corresponding the answers for all the assignment questions. So, let us start. The first question is for a 4 gigahertz downlink, if the satellite TWTA power output, that TWTA stands for travelling wave tube amplifier, that power output is 10 dBW. On axis antenna gain is 34 dB. This is on axis antenna gain, and the feeder loss, that is between the power amplifier and the antenna, whatever cable and connectors etc. that come, that loss is assumed to be 1 dB. Then the satellite EIRP on earth at 3 dB contour edge of coverage will be, there are 4 options given: 55 dBW, 50 dBW, 45 dBW, 40 dBW. Now, in this question you see it carefully. One is you have to calculate the EIRP with the power output available, antenna gain available and losses in between that is available, that is on axis antenna gain, and also from that you have to calculate EIRP with the antenna contour which is minus 3 dB. From on axis it is reduced by 3 dB. Now, in these type of things as well as in many other places, you will find some of the numbers or some of the information will give additional information. Here this additional information is 4 gigahertz downlink. Let us see how this sum is done. So, EIRP in dB on the main axis of the antenna will be the combination of TWTA power, that is power amplifier output, antenna gain in the main axis antenna gain, and the feeder loss. And let us see the picture. Let us say this is the TWTA power amplifier, its output is PT at the output point of power amplifier, and equivalent of all the losses up to the antenna is put as a feeder loss, this red color feeder loss. Let us call it TX feeder, transmit side, so it is called TX feeder. Similarly, receive side there may be feeder which could be called RX feeder, in this case transmit feeder. And then gain of the antenna, this is a parabolic antenna which has some peak, and that is on the peak axis, that is the maximum gain. So, EIRP maximum will be the transmitted power output from the amplifier minus the loss plus the gain, that is the maximum EIRP. But then it says that at 3 dB contour, let us try to understand what is it. What is the value? That is EIRP max on the main axis of the antenna is calculated as 10 watt minus 1 dB. 10 watt is equivalent to 10 dBW minus 1 dB and 34 dB antenna gain. So, it is 43 dBW, and at 3 dB from the peak, that is on axis, when it is reduced to 3 dB antenna gain, the pattern of the antenna is like this: peak sometimes and then goes both side, reduces. So, the gain when it is 3 dB reduction, that is half power point, 3 dB reduction, it is GT max minus 3 dB, and it says 3 dB contour coverage. How it looks like? Let us have a picture. Let us say India, and this is the center point of India, where center point towards the India where the satellite is pointing, satellite antenna, this beam is pointing, this GT max value will be available here. Let us assume, this is just an assumption, and from here the gain will be reducing, and this is the, let us assume this is the 3 dB contour, it is called contour. So, this one is GT max minus 3 dB will be on this contour. So, gain is reduced by 3 dB. So, therefore, the at minus 3 dB contour edge, the EIRP will be maximum EIRP minus this 3 dB. So, that is 40 dBW, and from your options you can see the correct option is the last one, which is D. Let us go to the second problem. Second problem is also a practical problem for your understanding of this contour coverage. a DTH terminal, that is direct to home terminal, is located at, let us say, Goa, and let us say Goa is minus 2 dB contour edge of satellite transmit antenna footprint, just like the previous one. It is, instead of minus 3 dB, it is minus 2 dB from the peak, that is satellite antenna gain. Assuming path loss difference is negligible for same C by N, how much DTH antenna gain is to be changed if it is shifted to Port Blair, that is at Andaman, which is at minus 9 dB contour edge of satellite transmit antenna footprint. So, we are imagining the footprint of the satellite antenna on India such that at Goa it is from peak it is 2 dB less, and at Port Blair it is 9 dB less. And what is asked, that you try to maintain the C by N same both at Goa and Port Blair, but the losses will be more because it is reduced. To keep the C by N same, how much receive antenna gain, that is DTH antenna gain, is to be changed? And the options for the answer is antenna gain has to be increased by 7 times, antenna gain has to be reduced by 7 times, antenna gain has to be increased by 5 times, it is to be reduced by 5 times. Here question is changed, it did not say whether it is to be increased or decreased, that you have to find out. Let us see. So, let us try to draw the similar type of picture, that is Goa is at minus 2 dB, somewhere here is the Goa assumed, and this is the center. It is drawn as a elliptical footprint, assuming satellite some imaginary position from where and the earth on the India, it will be elliptical footprint. Since it is not at the equator, it has to be elliptical, and then Port Blair is at 9 dB contour. This is that 9 dB minus 9 dB contour, somewhere here the Port Blair is. So, this is the satellite transmit antenna footprint. So, the gain here is maximum, and that is reduced to 2 dB here, and from here it is reduced to reduced to 9 dB here. So, station at Port Blair will receive minus 2 dB and minus 9 dB. So, 7 dB less compared to what is at Goa. Now, try to remember which says that C by N to maintain constant. Here Goa and Port Blair, both the places we want to maintain the constant C by N. And what is C by N? Is the C is that is, you separate out C, then it is EIRP from the satellite, losses and receive antenna gain, and N is the KTB, and since it is in dB, it is plus minus way it is written, and since it is at the denominator, all are minus. So, KTB is minus. So, this is C by N. Now, C by N at Goa and at Port Blair we want to maintain same. Now, for that EIRP from the satellite at both the places, it is same. This is maximum EIRP, and then the path loss is said that it is assumed the differential path loss from here and here, since the satellite is at 36,000 kilometer high, differential path loss is almost same. Differential path loss is 0, that is path loss is almost same. K is a constant, bandwidth is constant, temperature, noise temperature, let us assume that is also constant, because both the elevation angles are quite high. So, sky noise only it is seeing. So, therefore, the receive antenna gain has to be changed to take care about the reduction in EIRP, because transmit antenna is 7 dB is lowering the gain. So, therefore, the 7 dB it is lowering, you increase the gain of the antenna 7 dB here. So, maintain same carrier to noise ratio, antenna gain has to be increased, this has to be increased to minus 2 dB level. So, increase by 7 dB. So, 7 dB, the question was not in terms of 7 dB is equivalent to 5 times of the original one, dB you convert to ratio. So, correct option is C, that is to be increased. Let us go back to the options. C, antenna gain has to be increased by 5 times. Let us go to the question 3. Find the EIRP of the downlink operating at a 4 gigahertz. The antenna has effective aperture area of 10 square meter and 10 watts of power is given as input to it, input to the antenna. So, what is the EIRP? Now, there are 4 options given: 43.5 dBW, 43.5 dBm, 53.5 dBm and 53.5 dBW. Let us see. Gain in terms of frequency and antenna aperture is 4 pi AE by lambda square, and lambda in terms of frequency and velocity of light or electromagnetic wave in c square, f by c, that is f square by c square, and AE is already given. F is 4 gigahertz. You put all these values, you will get a number in terms of dB is 43.5 dBi, that is the gain. And the power is 10 watt, which you convert to dB, it will become 10 dBW. So, EIRP is power, transmit power plus antenna gain is 53.5 dBW, and obviously the appropriate option is D. Let us go back. Appropriate option is D. It is 53.5 dBm and we got 53.5 dBW. This is 10 watt. So, this was dBW. So, that becomes 53.5 dBW. Option is D. Let us go to the next one. Now, a receiver at 290 K is having noise figure of 4 dB. Receiver is at normal temperature and it has a noise figure which is mentioned. Now, question is noise power density of the receiver is, there are 4 options given with the different values dBW per hertz. Noise power density. So, this density is the spectral, that is it has to be divided by B. Noise power is kTB. So, since it is density, that is B is divided. So, it becomes kT, noise power will be kT. So, therefore, T has to be found out, whereas F is given, noise figure is given. Simple. So, receiver noise figure first 4 dB convert 4 dB and 290 K, the normal temperature is given, and the noise temperature is T0 into F minus 1. This F has to be in ratio. So, this 4 dB 10 to the power 4 by 10 290 into 10 to the power 4 by 10 minus 1, which comes out to be 438.45 K, which is equivalent to 26.41 dB K. Now, that we have got noise temperature. And noise power density is kT. It is then, since it is density we said N0, actually it is N by B. So, it is kT, K is Boltzmann constant, which is minus 228.6 dBW per K per hertz. Now, just I want to mention here that during our regular lectures we might have missed, sometimes we might have said it is dB per K per hertz. Please note that it has to be K value in terms of dB will be dBW per K per hertz. Just note that one. And this number always you have to remember, that is it is minus 228.6 dBW per K per hertz, that is K. So, this N0, if I want to do it in dB, then it will be K in dB and T in dB, minus 228.6 and T we have got 26.41. So, it comes out to be minus 202.19 dBW per hertz, and our options were 228.6, 170, 202.2, minus 100. C seems to be nearest. So, appropriate option is C. Here I just want to mention that many of the cases it is the nearest value you have to take for the selection. So, that was given this is 202.19 is the nearest value. So, that is why we have taken option as C. Let us go for the next one. This is much longish written, but the problem is very simple. The effective input noise temperature of a earth station receiver is 30 K. Effective input noise temperature is already mentioned. When the effect of noise contribution from the antenna and feeder were not taken into consideration. That means, independently noise temperature is 30 K. Now, if the receiver is fed from an antenna having a noise of 50 K, which is looking towards the sky, it is quite low, via a feeder which has loss of 2.5 dB, then determine the noise temperature of the receiver considering the effect of the antenna, the feeder noise contribution, and assume that it is 290 K is T0. So, initially it is 30 K. Now, that antenna is receiving the noise, antenna input noise or antenna noise is noise temperature is 50 K, and then there is a loss which is 2.5 dB. So, there will be contribution from the noise temperature which is coming from the antenna, and there will be contribution which is given by the feeder loss, and then that has to be added with the receiver noise temperature. Then we will get the total noise temperature, which are 4 options are given. Let us see which option we get. So, L is the loss for the feeder is 2.5 dB, which we convert to ratio 1.778, and then antenna noise when it is coming through the feeder, it will be reduced. So, that 50 K which is received by antenna, which will be reduced by this factor. So, it will be divided by this, and so it becomes 28.1 K, and feeder itself is generating a noise based on the normal room temperature. So, that is T0 into L minus 1 by L. L is that feeder loss, in these are all in ratio. So, it is 1.77. So, this value with 290, if you multiply L minus 1 by L is equal to 126.9 K. So, this is the contribution from the antenna after the temperature comes through the feeder, and this is the contribution of the feeder itself, and the receiver has its own noise. So, all these 3 are added to get the effective noise temperature of the receiver, that is 28.1, 126.9 and 30, which comes out to be 185 K, and then the appropriate option choice is a C. Okay, let us go to the next question. This also look longish, but you have to understand a little. Let me explain. There is a 6 gigahertz satellite uplink, and you know, in C band we have talked about that generally uplink is 6 gigahertz and downlink is 4 gigahertz. Here in this case we have assumed 6 gigahertz is the uplink, and it has following data. The earth station which is uplinking, its EIRP is 80 dBW, that is its power amplifier and antenna put together towards the satellite is 80 dBW. Earth station to satellite distance is 35,780 kilometer. Attenuation due to atmosphere is assumed to be 2 dB. Satellite receive antenna aperture area is 0.5 square meter, a small antenna. Satellite receiver's system noise temperature is 290 K. Satellite receiver's bandwidth is 20 megahertz. Determine the link margin for satisfactory quality of service if the threshold value of the received carrier to noise ratio is 25 dB. At 25 dB we are just satisfied, C by N of 25 dB, but now we have to find out how much more we are getting, above 25 dB how much we are getting. That means, what is being asked, that first find out the receives C by N, the uplink C by N, and then from 25 dB how much more it is. To get this C by N value, you need EIRP and then the losses, and then the receiver bandwidth, KTV, noises, etc. Since C by N. Let us see how it is we proceed. So, uplink frequency is given 6 gigahertz. First we convert that into we find out the lambda for that. The receive antenna gain in terms of lambda is 4 pi lambda square into AE. AE is already given, lambda we have found out. So, this number comes out to be 34 dB. The path loss is 4 pi r by lambda whole square, in terms of dB 20 log 4 pi r by lambda. By putting the value of r which is given there, lambda we have found out, 20 log of that is 199 dB. Atmospheric loss is additional loss, that is 2 dB given, and EIRP for the earth station is 80 dBW towards the satellite. So, the receive power at satellite is EIRP minus losses plus the receive antenna gain at the satellite, and this is EIRP already given. Path loss is 199 and miscellaneous loss is 2 dB, and the antenna gain we calculated is 34. So, received power is minus 87 dBW, and since it is C by N, so noise we have to find out. For noise, the received noise temperature is given, T is given, bandwidth is given, T is 290 K, bandwidth is given 20 megahertz. So, it is in dB it will be 10 log K T B, and by putting the value of K, T and B, in this case you have to put the value of K in ratio minus 130.96 dB. You can break it and make a K in dB, T in dB and B in dB, that also can be done. You will get always minus 130.96 dB. So, C by N then in dB, C is minus 87 and N is minus 130. So, C minus N is 43.9 dB. So, 43.9 dB is much more than 25 dB. How much more? That is 43.9 minus 25 is 18.9 dB more, and that is the option A. The first choice was the option A. So, this is how C and N separately calculated, and then C by. This is done in dB. Some places are in ratio. You have to maintain in one way, either do it in dB or do it in ratio and then come back. The next question is an LNB with gain of 12 dB, bandwidth of 150 megahertz and a noise figure of 4 dB feeds a receiver with equivalent noise temperature of 900 K. That means, there are two parts, one is a LNB, low noise block converter, and after that there is a receiver. So, low noise block converter, some details are given, that is the gain, bandwidth and noise figure, and the receiver, the noise temperature itself is given. So, determine the noise figure of the overall system. So, it is a cascaded system, there is a LNB and there is a receiver. LNB some details are given, receiver directly 900 K is given. So, cascading has to be done. So, let us see the receiver noise figure in ratio is T e by T 0, 1 plus T e by T 0, T e is 900. So, 900 by 290, T 0 is 290, becomes 4.1. It is written NF2, that is the second, there are two stages, LNB and receiver. So, the second stage, that is why NF2 is written. Noise figure of the cascaded system. So, the overall noise figure will be the first system noise figure, and then second system noise figure minus 1 by G1. So, this is the cascaded thing. Now, these are all in ratios, that is why small letters are written. So, that is 4 dB is 10 to the power minus 10 to the power 0.4 and NF2 4.1 you got. So, NF2 minus 1 4.1 minus 1 and G we had 12 dB. So, that is 10 to the power 1.2. So, the whole thing comes out to be 2.71. So, correct choice is D. Let us look at the choice. 2.71 was D. Next one. RF amplifier has 20 dB gain and 1 gigahertz bandwidth. Now, we have to find out what is the output noise power of the amplifier, and assuming there is a input noise source temperature is this. Let me read the question fully. RF amplifier has 20 dB gain and 1 gigahertz bandwidth. Hot and cold load temperature, there are let us say there are two temperatures T1 and T2, two load temperatures, and corresponding amplifier output powers are N1 and N2 are measured. T1 when it is connected to the load temperature 290 K, then the output noise power is measured as minus 62 dBm, and when the load temperature is changed to 77 K low temperature, then N2 is much lower, noise power measured after the receiver is minus 64.7. Now, with this type of measurement you can find out what is the noise temperature of the RF amplifier, and then if that RF amplifier is given 450 K as an input temperature, then what is the output noise power. So, for that case you have external noise which is coming as the input of the amplifier. You have to find out from all these measured figures what is the system noise temperature, equivalent noise temperature of the amplifier itself, and then amplifier gain and bandwidth is already given. Let us see how it is done. There are hot and cold two loads are there for this amplifier, which has a gain G, bandwidth B and equivalent noise temperature T E, and there is a power meter which measures. So, when this is connected towards a load which is T1, then power N1 is measured. When it is connected to the load T2, then another power will be measured, and from the ratio of these two powers you can find out what is T E, because these two temperatures are known and the power outputs are also known. Let us see. So, the ratio of the two measured power N1 by N2 is K T1 B into G plus K T E B into G. So, K G B are all common. So, it is T1 plus T E. So, when the input is connected to the cold load which is T2, again two noise, one is K T2 G into B and another its own noise K T E G into B. So, K G and B are taken out. So, you will be left with T2 plus T E, and since numerator and denominator both has K, G and B, they are cancelled. So, the ratio of these power what you measured is equal to T1 plus T E by T2 plus T E. Now, in this Y value is known because we know the value of N1 and N2, we know the value of T1 and T2. So, T E can be easily found out. So, T E is by changing the sides you can get T1 minus Y T2 by Y minus 1. So, let us put the values. Y is N1 and N2 are measured in dB. So, it is subtraction of that, which is coming out to be 2.7 dB. This is N1 and this is N2, and which if you convert into ratio it becomes 1.86. Now, these are all done in ratio, that is why we converted Y into ratio. So, T E by substituting into this expression, T E is T1 minus Y T2 by Y minus 1, this is T1 290 and Y is 1.86 and T2 was 77 K and Y is 1.86 minus 1. So, if you solve this it comes out to be 170 K. So, now we know that T E. So, this amplifier is now fully characterized, which is we know the gain, we know the bandwidth, we know the equivalent noise temperature of the amplifier. Now, the problem which says that at the input, now disconnect this, at the input if you connect a source temperature which is 450 K, then what will be the output noise power? So, output noise power will be the gain of the amplifier G K source temperature T S, this is not the system temperature, this is source temperature G K T S B, and this is the equivalent temperature which we have found out just now G K T E B So, this is at the input which is coming and this is generated by the amplifier, both together will give the noise power. So, if you put all these values of k, this is G, k and b, that is gain is gain, then this is k value, this is b value, and then if you take common it is T s plus T e. So, 450 plus 170. If you put all these things together and convert into dB, and then you will get some number which does not match with your result. So, you have to convert into dBm and get minus 60.7. You see minus 60 dBm, nearest value is minus 60 dBm. So, this dBW value will be 30 dB less than this, would have been minus 90.7 dBW, which was not there. So, the correct option is appropriate option nearest is D. Let us go to the other sum, that is in a satellite link operating in 11 gigahertz, the Ku band. The power received by the earth station is minus 126 dBW. The power amplifier of the satellite supplies 100 watts of power to the satellite antenna. Determine the diameter of the downlink antenna of the satellite. If the gain of the earth station is 1.7 dBi, very low gain, it is normally the value of a dipole. Dipole gain is almost comes to this number. Assume the downlink satellite antenna has a efficiency of 60% and the path loss occurred is 205 dB. So, what we have asked to find out what is the diameter of the downlink antenna. First, you have to find out what is the downlink satellite antenna gain, and then the frequency is given and efficiency of the antenna is given, we can find out the diameter. Let us see, there are suggestions which are, it could be 2.8, 8.2, 4.2, 2.6, various things. So, let us see which one is correct. Receive power P receive at the earth station is the transmitted power from the satellite, transmit antenna gain, receive antenna gain and minus the path loss. In this case only path loss is mentioned. These are all in dB, that is why plus minus. Now, in this except this GTX, which is transmit antenna gain from the satellite, all other values are known. So, GTX can be found out, you just change the side. So, path loss will become positive, all others will become negative. So, 205 minus 126, which is received, minus 20 minus 1.7 dB, that is receive antenna gain, 57.3 dB, that is transmit antenna, and then antenna gain is efficiency into pi d by lambda square, pi d f by c whole square, then that gain value is already available 57.3. So, in the ratio you can get it. So, in this f is known, d has to be found out, efficiency is known, c is known. So, d is 8.21 meter and our one of the option is given as 8.2 meter, which is nearest. So, B option is correct. Now, you can see the satellite antenna is 8.2 meter, this is satellite antenna, very big. Now, the receive antenna gain was very small, it is a dipole. That means, if you want to have a handheld receiver, then your satellite antenna, assuming all other powers and losses are same, your satellite antenna diameter is very big. That is, if you want a cell phone to be used, cell phone type of device to be used, which has a very low gain antenna to be used with satellite at 36,000 kilometer high, the satellite antenna has to be this big. Now, if you want to reduce the satellite antenna, you have to increase the gain. So, in VSAT we have almost 30 dB here, in VSAT or DTH we have 20 to 30 dB, this value here. So, you can replace, assuming all other numbers remain same, you can replace that and you will get the d value of the satellite is much smaller, it will come to 1 meter or so, or around that. So, that is all for today. So, we will see for the subsequent week next week. Thank you very much.